Okay, now I'm going to talk about, well, we are going to do Hooke's law today. Okay, now Hooke's law is about springs. Okay, let me show you this. Okay, now, okay, so I have three springs and I have, sorry, there are three springs. Now, have a look what's happening if I put a 50 gram on one of it. Okay, now the spring became longer, it's extend, okay, because there's a force applying to it. Okay, so if I put 100 gram on the other spring, okay, what's happening is it become longer again. Okay, now if I put a 250 gram on there, it become longer. Okay, so this is called the elastic region of the spring. So what Hooke discovered, what this guy discovered was, okay, so for spring, okay, now the force, okay, applied to a spring in newtons, okay, and well, sorry, the idea is, okay, okay, sorry, I should, okay, we call this, if we plot a graph, okay, of the force applied to the spring and the extension of the spring, okay, it will be a straight line in its elastic region. Okay, it will be a straight line. Okay, so it will be something like this. Will be a linear relationship. Okay, say in meters. Okay, now the gradient. Okay, so gradient. So if I put this equation in mass form, it will be force equals to kx, where x is the extension. Okay, now the gradient k, okay, is called spring constant. Okay, so it's a property. It indicates, how do I say it? To make it simple, it indicates the strength of the spring. Okay, the higher the spring constant, the well, the harder to make it to extend. Okay, so um, actually everything has a spring constant. For example, uh, not only springs. For example, a piece of metal. Okay, if you have a metal rod, if you pull it really hard, to some extent it will be longer a little bit. So it will act as a spring. So almost every object will act as a spring. So almost every object they have a spring constant. Okay? So that's Hooke's discovery. Okay? But what we can do about it is, uh, um, sorry. Okay, so you need to be able to use this thing. Okay, so the spring constant k is the gradient here. Okay, now let's find out its unit. Okay, remember how to find the unit of the gradient? Okay, now the unit of the vertical divided by the unit of the horizontal. Okay, so the unit will be newtons divided by m. Okay, so it is newtons per meter. Okay, so for example, if the spring constant is, okay, for example, if the spring constant of a spring is 10 newtons per meter, it means I will need to apply 10 Newton force for it to extend a meter longer. Okay? If it's a minus, it means compression. So, yep. So let's okay. Now let me show you. Let me show you the spring again. Okay. Now, say if this time, say, let me show you this. Okay, if I put, say, let's make spring 3 harder. Okay, almost double than before. So if I put 100 gram here, okay, since spring 3 is harder, okay, it's double the strength of spring 1, it will, if I put it here, well, more than double actually, it will deflect, the spring 3 will deflect less. Okay, spring 3 will have a higher stiffness. So we call it, yes, yeah, higher stiffness. Okay, now, yep. Okay, there are more to springs. However, we just that's all we have to know for now. Okay, now then, yep. Okay, actually, okay, I made a mistake in the previous part. Okay, now the spring constant does not tell you the strength, it tells you the stiffness. Okay, so how many newtons to make it to extend per meter? Okay, it's called the stiffness. Okay, strength of a spring indicates the maximum load it can hold, but we're not going to do that now, so just don't worry about it now. Okay, now, okay, have a look at that again. Okay, now say if I put say if I apply a force to the spring. Okay, so what happens is the spring, okay, there will be energy held in the spring. Okay, because when I release it, well, I do that right. If I release it, it will move. Okay, so I put non-friction there. Okay, so in order to be okay, in order to have a spring compressed or extended, it holds energy. Okay, because when I release it, it returns to its original state. Okay, but let's say how do we find? We call this energy the elastic potential energy. Okay, it can be found under a force displacement graph. Okay, since the area under the graph. Okay, because we have newtons and meters here. Newton times meters, Newton meter will be in terms of joule of energy. Okay, now but also there is a formula. Okay, so we call it elastic potential energy or spring energy. Okay, or spring energy. Okay, now if I want to calculate the spring energy, say this is my x. Okay, now the vertical one will be my kx. Okay, the area under the graph is a triangle, so use my rule for triangle, half, okay, the base times the height. Okay, then you have the spring energy equation, your half kx square. Okay, this is for spring energy. Okay, so write this down, write the equation down in your notebook.